Okay, so hello everyone. Today we're going to talk about an evaluation that we've made lately concerning the OpenStack internal messaging system, and especially in the context of edge computing. So who's here?
I'm here.
Okay, me too.
I'm Ken Giusti. I'm a core committer on the Oslo project, focusing on messaging, and I am an enterprise messaging developer at Red Hat.
Hi, I'm Javier. I'm a research engineer at the INRIA, the French Institute for Research in Computer Science, and in collaboration with Orange Labs.
I'm Mathieu Simonin. I'm a research engineer as well at INRIA, working on distributed system in a project called Discovery. And the three of us are basically also contributor to the Fog Edge Massively Distributing Working Group, which is a working group within the OpenStack community, working on massively distributing OpenStack and gathering people regarding these use cases. We have a working group tomorrow, Wednesday, so feel free to join if you are interested in the topic. So talking about edge. A classical model for edge computing regarding telco infrastructure is something like the one is described in the slides here. So you have a bunch of sites that are placed all along the path from the core of the network to the edge of the network. And basically those sites are organized depending on how far they are from the core network. So for example, you find some regional sites, let's say like they are 10 milliseconds far from the core of the network. You have local sites that are maybe, I don't know, the number may vary depending on the actual infrastructure, but the regional site can be 50 milliseconds far from the core of the network, and so on. There are different challenges when working on this kind of infrastructure, and if you think of an application that you want to deploy on this kind of infrastructure, your application will likely, you would like your application to take benefit of the distribution of the resources that you have in this kind of infrastructure. So basically, you will have maybe different parts. Some parts will be deployed close to the user, in other words, at the edge, to achieve maybe some low latency requirements that you will need. And some other part will be, for whatever reason, deployed maybe closer to the core of the network. If you would think of the resource manager that is responsible for managing your applications, it needs to be scalable enough to span the different sites from the core of the network until the edge of the network, or at least a subset of the sites from the core until the edge. So the scalability for the underlying resource manager is very important. It's the key challenges in edge computing. Another challenge is what we call here locality. So since you have different parts in your application, one part that are maybe close to the edge and one part that may be close to the core of the network, you don't want these two parts to over-communicate between each other, because in this kind of architecture, communicating between these two parts may be costly due to the presence of latencies, or maybe loss or some network constraint that can exist in this kind of architecture. So there are other challenges, but we will focus today on these two challenges, scalability and locality, and especially in the context of the messaging layer of OpenStack. So when it comes to scalability, maybe most of you are familiar with this challenge. It means increasing the number of messaging agents, communicating agents. For locality, what we call locality here is the ability to keep the traffic in the same latency domain as much as possible, not trying to mitigate communication over one, basically. So if you look at OpenStack, there are different control traffic that are happening. There are API traffic due to APIs, you have traffic due to database management, and you have also traffic due to remote procedure calls. And in this talk, we will only focus on remote procedure calls. So the scope of the talk is the OpenStack remote procedure calls in the context of massively distributed cloud. We'll need first some baseline about Oslo messaging before diving into the evaluation section, and we'll conclude with some lesson learned and conclusion on what we will do in the future. So I give the mic to Ken.
Thank you, Matt. So I'm going to take a minute and discuss really the concrete aspects of what we're evaluating here. What do we mean by OpenStack internal messaging, right? This is internal messaging, not visible to the user. Take a project like Nova. It's made up of discrete processes that can be distributed throughout the infrastructure, right? They need a means to communicate, inter-process communication. This inter-process communication is provided by a library of remote procedure call utilities built on top of a message bus, RabbitMQ, right? We're all familiar with that. This is what we mean by this domain that I've highlighted here. This is what we mean by the internal messaging that we're going to evaluate. Now, this library of RPC, procedure calls over a message bus and message bus integration is provided by Oslo messaging. All right, so it's a common implementation that all projects can leverage and use. It's part of the Oslo project, right? An Oslo project maintains a set of Python libraries for general purpose usage that other projects can use rather than reinventing the wheel. We have projects for logging, Oslo config, Oslo DB, and Oslo messaging. And the Oslo messaging is the library that provides the APIs for messaging services, including remote procedure call. And as I said, it's inter-process control messaging in OpenStack within a project, inter-project. But another aspect of Oslo messaging that's not as apparent is that it is an abstraction. It hides the actual details of the message bus, the drivers, the interfaces, which means that we can test different message bus architectures. So quickly, what is a remote procedure call, right? It's a synchronous request response pattern. A client needs to perform a function on a server that's remote across the message bus. The client creates, and the API, it's actually functional. It makes a function call, which is translated into an RPC request message, which is sent out over the message bus to the proper server. The server then executes the process or the function, generates a return value, and sends a response, right? So it's a synchronous exchange between two parties. If the server is not there, the client should fail, right? The call should fail. So they have to both be present in real time. So we have three different flavors you'll see in our evaluation of RPC. The call being the most obvious one. We also have a lightweight cast, which is like a one-way directional transfer of information. You send a request to a server, but there is no response. And then there's fan out. And what fan out is multicast. A client needs to send a request to multiple servers. And it relies on the message bus to take its single message and duplicate that over the message bus to all the servers in an efficient way possible. So kind of touching on this, how does a message get to the proper service? By addressing, right? So each project has its own servers that it assigns identifiers to, names to, addresses to. And these represent the functionality these servers provide for the clients, right? So in our example here, we have a server, RPC server that represents service A and a RPC server that represents service B. These identifiers, we call them targets. It's an abstraction, also messaging. These targets are used as subscriptions on the bus. Essentially, the servers go to the bus and they say, I'm interested in any message that's destined to service A. So when a client needs to send a message to service A, it puts that as the destination address in the message, and it leaves it to the message bus to deliver that message to the service as efficiently as possible, right? So while a service can have its own unique address, one service out of the entire cloud, right? Often, multiple servers, identical servers that perform the same process will sit on the same address, and that's a purpose for load balancing, right? A request can be load balanced by the message bus to go to only one of these parallel services. Also, that sharing of addresses can be used for multicast, right? Remember that I send one message out to a particular destination address or target, boom, goes to everybody. Now here's the real crux of the evaluation. Remember I said Also, messaging provides an abstraction layer. It goes a little further than that. It also provides support for different messaging technologies in addition to Rabbit. Now, what we're doing here with Fog Edge, you think about it, it's a distributed architecture, right? Wouldn't it be great if we had a distributed message bus that fit Fog Edge, right? Would it be better than a broker, right? Would it be better? And it's not better than Rabbit. It's better than any type of brokered architecture, right? This is what we're evaluating. So we have Rabbit, which is based on AMQP 09, which is a draft of the standard, right, a pre-draft. It's like QPD was based on 010. These drafts of the AMQP standard required a broker intermediary designed in the protocol. It was client-server protocol, where any two communicating parties had to send a message to a queue on a broker before sending it across. There were no direct communications. And as the AMQP technical committee was finalizing 1.0, then we got things like IoT, right? We got things like microservices. We got things like Fog Edge, right? So building a protocol that requires a central broker may not work well in these more distributed, high-scale messaging environments. So the 1.0 standard makes the broker optional. It just describes a protocol for transferring messages between two peer entities. And that's significant because we can do message buses that are different than brokers. Additional, augment brokers, not replace brokers, but augment them. Augment them in the way that brokers can be used in the message bus for queuing services, but they're not necessarily used for the transport. We can distribute the transport. Now, we're going to be looking at a distributed message bus. It's built on the Apache Cupid Dispatch Router project. This is a project to build a distributed, high-performance, scalable message bus that's fault-tolerant and basically does your dishes and walks your dog, does everything, right? So we're going to evaluate the behavior of this RPC domain that we're talking about in the Fog Edge context across these two different approaches. Now, I could talk about the Apache router for like an hour, and I did that in Barcelona. So I'm just going to gloss over it. If you guys want to learn details, I would suggest you watch that video because it goes into more than you want to know about the router. So here's my crude attempt to draw a Fog Edge, right? Let's look at the differences in the architecture of these message buses, right? So we have a core network, we have a regional site, we have a local site. We might have some regional services deployed at the regional site and services deployed at the local site, right? And RPC clients that need these services. But the broker approach, the broker architecture is always going to be centralized, right? Those messages have to flow through the broker as per the protocol. So we get in a situation like this. Our RPC client needs to invoke a service on a regional site, but it has to be forwarded back to where the big hardware is running this big broker cluster, right? So you get kind of a non-optional path. And it's exacerbated when you have, like, say, two communicating message passing entities on a local site that have to go across cloud to communicate, right? And the problem is that a broker architecture, whatever the broker is, a broker architecture does not understand least cost path, all right? It doesn't understand that these two things would be better off communicating because they're local rather than going back to it. That's where it differs from the router topology, right? So the dispatch router, it's meant to build a message bus by distributing and deploying these routers at your various sites and connecting them by TCP. The rest is fully dynamic. It runs a protocol where it learns these addresses. Remember the service addresses I was talking about? It learns the service addresses and computes the shortest path between an RPC client and the destination server, right? It's based on a Dijkstra algorithm. These are all concepts that the internet community solved a long time ago, but it's built on the same thing. Now, what we observe here is that messaging can now use, when we say least cost, a more direct route. Now, you'll notice I don't draw queues here because there's no queues here. This transfer is point-to-point, end-to-end, and it can be streamed. So large messages don't have to be queued. Multi-frame messages can be streamed across the message bus. The other thing to notice is that it is end-to-end, such that if the RPC client attempted to send a message to an RPC server that wasn't there was no address for it, well, what would happen in an IP router? You'd get an unroutable message, and that's exactly what happens. It'll fail immediately. The client will be told by the message bus, I don't got anybody, try again later. here's the case that's really interesting, right? Now we have a local site. We have two communicating processes that don't involve the rest of the mesh. If we imagine the same thing happening on this other local site, now we have parallelism. So two things that happen here. First of all, you have much lower latencies. And the second of all, you two have true aggregation and parallelism in the message bus. Now, let's talk about how you test this. How do you test a message bus that's distributed across Fog Edge? Well, you can't with any particular project, right? We needed a way of running a lot of traffic and control patterns. So we couldn't do that with, like, say, deploying a Nova or deploying Neutron or something like that. We actually used a tool called the Oslo Messaging benchmarking tool, which benchmarks Oslo Messaging. But actually, it's a load generator that generates a distributed load. It consists of a bunch of RPC test servers and clients built directly over Oslo Messaging. So they're acting the same way as these other applications. And you, as the tester, deploy these servers and clients across your message bus. And then you use a CLI command, a controller, to issue tests for these things to fire off and generate traffic. And at the end of these tests, the clients report back to the command line tool all the metrics, including aggregate throughput and latency distribution, right? So this is cool, but it only goes part way because the deployment of the message bus, the deployment of all these clients, it's a manual job with OMBT, right? Couldn't work for us. So that's why we brought the OMBT orchestrator. We developed this. And its job is to run a test soup to nuts, totally automated. It deploys the message bus as configured for the test. It deploys the clients and servers as configured for the test. It uses OMBT control to run the traffic test, but it also not only reports the metrics from OMBT controller, but it also monitors the health of the message bus, things like CPU utilization, TCP connections, and memory load. So, I've talked now. Oh, by the way, that's of course all open source. You can get it from GitHub. If you want to reproduce these things, you can do it yourself. And I'm going to hand it off to Javier to actually talk about what was observed.
Thank you. Now we have a better idea about RPCs. We will talk about scalability evaluation. First, let me explain a little bit how we worked. We defined a test plan that is available on the OpenStack website concerning the massively distributed RPCs. We have defined 6 scenarios, synthetic and operational, to evaluate 2 drivers, the router and the broker RabbitMQ. And we focus on the 3 common patterns, cast, call, and fan out. All the evaluation was performed on the Grade 5000 testbed that is a research facility in France. Now let's focus on the 3 first test cases of this test plan. We have 3 synthetic scenarios. The first one is a single large shard distributed target in which we have a lot of producers sending all the messages using only one target to the consumer. The idea here is to scale the number of producers and have a constant throughput and answer the question how big a single target can be. In the second case, we have a multiple distinct distributed target when we have one producer and one consumer and a dedicated target. This time, we want to evaluate how we can scale the number of targets and how many targets can be created. Finally, in the third test case, we have a single large distributed fan-out when we have only one producer broadcasting messages to several consumers. Here, we want to answer how large a fan-out can be. For that, we have a specific setup when we define several parameters, including the number of calls, of agents, producers and consumers, and the call types. 2 parameters are particularly interesting here. The bus topologies, because we test the RabbitMQ and QP dispatch individually, and also we construct clusters of 3 and 5 brokers for RabbitMQ, and in the similar way, a complete graph of routers of 3 and 5 elements. Additionally, we also test a ring of routers up to 30 routers, including latency between routers. We have 2 configurations for the bus load, one light with 1,000 messages per second, and one heavy with 10,000 messages per second. So basically, this is a command line utility. When we define a test case, we send messages, or eventually we can perform campaigns to test these configurations. Let me show some results concerning the system metrics. Here we have the memory consumption for the first test case, for the RPC call. We can notice basically 2 things. First, routers perform better in terms of memory consumption compared to the broker. For example, on my right, we have less than 5 gigabytes of consumption for one router, compared to more than 25 gigabytes that is used to perform a use case for the broker. Another interesting thing is that we also identified the maximum number of supported agents for each driver. In the case of the broker, we have around 6,000 clients compared to the 8,000 clients of the router. This phenomena is the same for the configurations of 3 clients and 3 drivers and 5 drivers. But the load of memory is distributed between all the routers or brokers. In the same way, the CPU consumption for the test case 1 shows the same thing. The consumption is much bigger for the case of the broker, because we have to use up to 20 cores for brokers for one driver, compared to only 3 cores for the router. And the behavior is similar for the configurations of 3 drivers and 5 drivers. The results of system metrics are similar for the test case 2 and the test case 3. But we also evaluated the latency that is defined for us as the time a producer requires to send a message and receive back the answer from the consumer. Here, for example, in the single large target, we can observe that there is a constant latency for the case of routers in several configurations, 1 router, 3, or 5. But the latency increases for the broker. In the second use case, for multiple distinct targets, we can observe that both cases are similar. And finally, the latency for scalability in the test case 3, we observe that both situations, drivers and routers, are similar, but again, the routers are slightly better. In summary, we can say for all 3 cases that routers are lightweight in terms of CPU or memory consumption, but we also evaluated other metrics like network connections, and we verified this statement. If we focus on each test case, we can say that for the first test case, that implicit parallelism is observed only with routers due to the single queue that is required in the case of brokers. Then, for the second use case, multiple distinct distributed targets, we have a similar behavior for both drivers because of the short buffering. And finally, for the single distributed fan out, we can observe that router is less sensitive to the size of the broadcast. Now we will pass to talk about the locality evaluation with Matt.
Thank you. So now in this part, we will only focus on locality aspect of the message bus, not the scalability. And as a reminder, now we are going a bit more multi-site, meaning that now producer and consumer are spread over different distinct locations. Locality, as a reminder, is trying to keep the traffic as local as possible in the same latency domain. So we'll review some strategies that you can use when you want to deploy multi-site message bus. And then we will see that there is something unique in the router that can give you some guarantee, strict guarantee or strong guarantee on the locality of your message delivery. The first, maybe I will skip it because we are maybe a bit behind the schedule. This is a centralized message bus. So the idea here, in a few words, is to deploy a bus in a centralized place, and all your consumer and producer of every site are connecting to this central place. If you think of producer in site 1, if you do care about locality, you want your message to be consumed in site 1 as well. Okay, so there are some parameters to do that, to do so using Oslo messaging, but they are very not practical to tune, because it depends first on the workload, actual workload you have on your site, and it depends on the actual latency you have between sites. So here, if you want to have some locality here in the centralized case, it's kind of difficult. As Ken mentioned in the first part, if you have a producer in site 2, here the message pass, the message followed by the pass followed by the message is suboptimal, because it will go first to the site 1 and then maybe go back to the site 2 to be consumed there. So you will pay twice the latency of the network. Okay, so this is not a very good strategy to achieve locality here. Another strategy is to shard your message bus. This is something that is used in Nova Sales, for example, Nova Sales V2. Sharding the message bus consists in having distinct message bus deploy in different sites, and having in those sites consumer and producer local to the site. So there is something very nice about this, is that in each site you have a strict locality, meaning that once a message is issued in one side, it remains in one side. So by design, you have a strict locality in the message delivery. There is one caveat here. Usually, when you do sharding, you had a top layer which is responsible to hide those sharding, which makes the sharding transparent to the user, for example. And the caveat here is that if you want to route a request from this top shard to one of the consumer in one shard, you have to keep a consumer index saying, okay, I want to send a message on this consumer. You need to first figure out in which shard is your consumer and send the message in those shard, and then it will be consumed there. So it means that the routing is different to your application. Okay? An alternative using router is to use a tree of routers that maps the hierarchy of the shard. And here, using router, they are routers, so they are able to route messages. So routing is now transparent to the application. So basically, if you want to send a message to one consumer, you just post your message to the first router, RDO, and it will figure out how to route the message until it reaches the right consumer. So now routing is transparent to the application, but it raises an issue, a problem is how locality can be ensured here, because now you don't have the strict locality as you have with sharding. So how locality can be ensured in this kind of deployment? So to answer this question, let's consider a more general case where you have different sites. different producers, different consumers on those sites, and you have routers on each site that are linked. In the picture, they are linked using a ring topology. And basically, a router mesh provides you two levels of locality. First, a router mesh can provide you what we call strict locality. It's also known in the Qpid dispatch project terminology as the closest mode. In this mode, local consumers are always picked over remote consumers. In other words, if you look at site 1, if your producers are in site 1, if you go for the strict locality mode, only the consumer of site 1 will get the messages. There will no messages flowing to other routers and other consumers there, if you go for this mode. One drawback of this method is that maybe the local consumer backload will increase during the time because you need to pay attention to scale accordingly to the workload your consumer. Okay, there is no load sharing between consumer of other sites using strict locality. That's why there is another mode of locality, which is load sharing. It is also known as the balance mode. In this mode, your routers are able to share the load between remote sites. How does it work? A cost is basically associated to every consumer, and the consumer with the lower cost is picked. And the cost is dynamic, meaning that for every messages, a router will compute a cost and see where it should send the messages according to the cost it computed. The question now is, if we go for the load sharing mode, how is the locality of the messages? So to answer this question, we have some graphs here in an experiment. Let's consider some site. We goes up to 30 sites here with some consumer and router, and we try to evaluate the locality in the message delivery in this balanced mode. We evaluate the locality regarding two parameters that are the message rate and the inter-site latencies. As you can see on the top graph, if you increase the load during the benchmark, if you increase the load, the more load you have, the less locality you have, meaning that messages under high load starts to be offloaded to remote sites. This is expected, actually, because if you increase the load within a site, you are actually increasing the backlog of local consumer, and the size of the backlog of local consumer is used to compute the cost for that consumer. So so the router will ultimately choose to offload message to remote sites. The second graph shows you the impact of the latency between the sites. So here, if you increase the latency between your sites, the more latency you will have between your site, the more locality you will have. This is kind of interesting. This is expected also because actually, the more latency you have between sites, the more chance you have to have some message in flight between two sites. And messages that are in flight are also accounted into the cost. So the cost is virtually increasing when you are increasing the latency. So a router will choose frequently to send message locally rather than remotely. So that's why we observe this behavior. As a conclusion for this, first, the cost is dynamic, and the load sharing mode of we just discussed is locality aware. It means that local consumers are always preferred over remote consumer. At some point, the router may decide to send remotely messages, but it doesn't happen much under usual workload. Here we have some heavy workloads, but under usual workload, you can expect your load sharing mechanism to be locality aware. So as a conclusion here for this part, this is kind of early work we are currently doing under the umbrella of the for-gauge massively distributing working group. Is we are trying to think of how we can leverage this routing mechanism, this locality feature and scalability of the router mesh within OpenStack. And the idea that come out is that let's start with a high availability OpenStack. So meaning that a high availability OpenStack is an OpenStack where services can be replicated. And there are some mechanisms to share the load between them. Let's start with that and place the replicas of the services on each site. So basically what we have here in the picture is one single OpenStack that is, whose services are replicated across sites. And we use a shared bus to link all the things together. What you gain by doing that is that you gain RPC localities. So for instance, when your Nova conductor receives if you want to send a message to a Nova conductor, the one that will be handle the request will likely be the one that is local to your site, according to what we have just seen before. Okay, so you will have some locality at the RPC level, but we perform some initial tests about that, but there are some performance impacts still. Everything is not perfect, and this is mainly due because we don't have APIs locality, meaning APIs here are calls randomly across sites. So we need to do the same thing for APIs as we do for the RPC, and we also need to do the same thing for the database. So database is non-local here. We don't know exactly where the request goes and where the states are stored. Okay, so there are some specific work in the working group that address this aspect of the database. So, and that's it. So, as a conclusion today, what we have learned. First of all, we have learned that Oslo messaging supports two implementations for the messaging layer. So first is AMQP 09, which with the familiar driver RabbitMQ, and AMQP 1.0, which is the new driver leveraging the QP dispatch router technology, for example. In centralized deployment, in terms of scalability, you get similar scalability, but what is important to note is that routers are lightweight and achieve lower latency, especially under high load. This is especially interesting when you go at the edge. The fact that routers are lightweight, you can afford to deploy them at the edge more easily. For decentralized deployments, a router mesh offers you different guarantees in terms of locality. So locality is probably something that is application dependent. So depending on your application, you can choose which locality guarantee you would like to have. And then we presented a first deployment of OpenStack that can leverage a router mesh and achieve RPC locality. So all this work is done under the umbrella of the FEMDC working group. So I just remind you that we have a working group next Wednesday. So it's tomorrow. If you have time and if you are interested, feel free to join. I've put here some links. So if you are interested on the raw results, they are all here. And you can feel free to check them and maybe run them again if you want. So thank you.
If there's any questions, we'll run over a little bit, but I'm sure there'll be enough beer for us all afterwards, except maybe for McKelly. Sorry. Any questions? Comments?
Do you know of any, like, large is relative, but large production OpenStack clouds that are using a dispatch router?
Well, I'm sorry. Is there a mic?
There's a mic here.
The question, oh, there's a mic right there. But I could probably repeat the question, right? Are there any current deployments of the dispatch router in production? you'll understand that I say I can't really say anything about that. Sorry.
We don't count.
That means there is.
Well, I didn't say that.
No, it's just, you know,
It's not something I can talk about.
yeah, most everybody uses Rabbit.
Of course.
I don't know if that's because everybody's been using it forever, so it's kind of common.
Well, it pretty much solves the problem for most people. What we're trying to look at is maybe there's these architectures that we can leverage, going forward, and maybe there's use cases we can build around them. Like this is food for thought, right? For teams like Nova and Neutron to kind of evaluate this and see if they can leverage it in a way to enable their fog edge goals, right? So any other question? Yeah.
I'm kind of curious if you happen to know like what has changed since in the past when like 0Q was kind of the old, I guess, option for doing something like this, because I know a lot of people are really interested in getting away from like a brokered messaging system.
Sure. Well, there was 0MQ support in Oslo messaging, but unfortunately the developers that maintain that have left, and it's bit rotted a bit. So we don't really have functional ZMQ at this point, unless somebody's willing to step up and start contributing and maintaining that code base. In terms of comparing a protocol like AMQP 1.0 or this router mesh of ZMQ, is there's a lot as Matthew had mentioned here. There's more dynamic aspects to a router mesh, right? Things we didn't go into here, like fault tolerance. Right, if you have multiple connections between routers and the connection goes down, there's a dynamic routing protocol that will route around that, right? Whereas when you get something like, I'm no expert in ZRMQ, but what I understand is that you rely on the HTTP transport, or I'm sorry, the TCP transport to always be, enabled there.
It's more about that this technology has sort of like filled in some gaps that ZRMQ had, because I know that there are a lot of people that wanted to move to something like ZRMQ, but they couldn't, like, because there was just some major problem with it.
Well, there's some difficulties because it's a true point to point. It's I think maybe if you want to certainly weigh in because you're more of an expert than I am, but things like multicast.
I don't know about the code much.
Okay.
Somebody else was writing that piece of code. I guess we were always hesitant to push it too hard, I think.
Yeah, like the company I used to work at, we wanted to use it,
Right.
and there were just issues that I don't remember the details about. So this is pretty cool that maybe things are at a point where we could really, like, people could really start using these purpose systems.
It's more of a,
Everybody wants to.
yeah, there's a problem that we have to look at as a community is we always think of messaging as queuing, right? And we have to kind of break that model in our mind. We use queuing when you need to use store and forward. When you're doing things like notifications, you can use queuing. Actually, there's a Kafka driver that has been in the works forever, but it is seeing some love and should be production ready in a couple of releases. There are developers working on it. That can also be used for store and forward when you're doing notifications and billing, right? So you can do Rabbit queuing, that's what you need it for. But for transport, especially synchronous transport, that's the idea of this distributed message bus, right? So queuing is going to be a service on that transport. You put a queue, a broker, or Kafka inside that message bus, and those entities that need to queue things, need to store things, will have an address for that, and the message bus will route to that resource. So it becomes more of a resource than a transport.
Yeah, I'm sorry. I think I understand that. It was just that, like, there was no viable, like, production option for not using Rabbit back then. I mean, this is years ago. So I was just wondering if anybody happened to know what's changed, or, like, if this technology is just that much better or something.
This is pretty interesting. I don't know.
Options that we had in OpenStack.
Yeah. I recommend there's a slide there where I had a presentation from Barcelona, if you haven't seen it. We deep dived it, and we explained a lot of the things I've glossed over, like management, right? How do you manage a mesh, right? You can't really manage a 0MQ connection, right? But how do you, trace messages through that? How do you see faults? How do you see the routing table reconfigure, right? We can do that. There's a graphical console and a management entity that allows you to manage the message bus as a single entity. So there's a lot of aspects that you want to use in an enterprise system that we really didn't go into here. So Andre, do you have a question?
Yeah. So thank you for a great presentation, by the way. I really enjoyed it. I looked at, listening to the results, I saw very positive results, and I was thinking, what is the price we pay? There must be some drawbacks, some flip side to this the routed architecture or the distributed architecture or the decentralized architecture. I only see benefits here. Is there a price?
This is a pretty good question.
Yeah, you can show messages. If you're using the pure mesh, right? If you try to use a notification over this and there is nobody listening for that notification, which is a valid use case, it will fail, right? And also, I don't know if you'd call this a problem, but it's something we haven't dealt with really too much in the OpenStack community, is that now it's a point-to-point protocol that recovery is a part of something that the clients have to handle. So if I want to send you a message and you're not there, right, and I notify that, I know I can resend that message. Do I want to? Right? When we have a queue, we have a broker, we send that message, if the broker's there, it gets queued, we don't know where it goes from there. It may never get to a service, then that becomes kind of a stale message. Application's just timed out. Right? But now we have the opportunity not only to do this, but also do flow control. Right? I can take 10 messages, and once the server backs that up, credit will go end to end, and it will prevent the senders from sending. But how do the applications deal with that? Right? They're not aware of credit. So these are some things we'd like to surface. I'd personally love to surface this in Oslo messaging if I can. But so there's different ways of thinking. Downsides? I mean, you guys used it.
If you want my opinion?
Please, yeah.
I haven't seen any downside yet, but we haven't tested everything yet. Especially resiliency, as you said, usually if you kill a link, the router must be reconfigured, but it's based on OSPF, which is maybe...
Well, it's not OSPF, but it's a link cost. It's OSPF-like. It's not running OSPF.
Yeah, it's based on... So we don't know everything yet, but so far it's kind of working well, actually. All the tests we've made, it's pretty good. And so we haven't tested resiliency. We haven't scaled that much. We were talking about a ring of router composed of 30 routers. We expect to go beyond that point, but so far there was no drawbacks.
Just out of curiosity, the problems you mentioned, like the application level recovery and the application level flow.
Go to the mic, please. The recording. Any questions?
Dis donc, on a des questions. On a des questions.
Just out of curiosity, you mentioned a class of problems that the applications had to deal with when there's a broker in between, when there's no longer a broker in between.
Yes.
Which is the application managed error recovery or potentially flow control issues, all that.
These are, by the way, these are concepts of messaging that exist even across different implementations. They're endemic to the messaging the solution.
Right. I
problem domain,
understand.
rather.
I'm just asking, I was just wondering, don't you have those similar sorts of issues even when there is a broker, or is that?
Yeah, the broker does a lot of buffering for you, right? So it does a lot of buffering for you. These queues are meant to be big, meant to hold a lot of stuff. You have a lot of clients sending messages. They have to set a time to live. They have to expire, right?
Presumably it imposes some flow control back on the clients?
Yeah, there is different, the standards do provide flow control from a queue too. But it's not that immediate kind of flow control end to end. It's to the buffer, right? It's to the queue. If the queues, I'm sorry, we're getting somebody yelling at us. We have to kill it. I'm sorry. Well, let's talk.
Yeah.
All right. Thanks. Thank you, everyone.
Thank you.